Okay, so in this video, we're talking about the electronics of the battery cart. Now, this video is not going to be super in-depth simply because I don't have the time to explain every single little thing, every single reason why I did what I did. But I will try to cover the big pieces so that way if you get confronted by a judge or another member of another team, you could explain what's going on. Now, from...
You could email it to us, and then we just read it off.
Well, that requires more work on my part, and working 40 hours a week plus 25 hours a week of school plus 5 hours here.
Oh, okay. Well, I thought that you already had it like typed up a lesson plan, and then you could just email it to us.
No, I do have lesson plans for other things, but because I've spent so much time working on this battery cart, I haven't really had time to write up what I've been doing. I've mostly just been doing it. Well, money's not really important at this point now, is it?
Nah.
So,
just plays with stuff.
Now, for the people watching this video, at times you will not see my face because I have to turn my computer to show the people that are actually with me, so you probably see their faces. You'll be stuck looking at Justin probably most of the time because Alexis is going to be a little bit out of the shot. Good, how are you?
Why would I be in the shot?
No, because my camera's right there.
Oh.
And I'm going to be turning my laptop to show you guys stuff. Okay? So, the first thing is this. This is the circuit diagram for the simplest board on this whole project.
Yeah, I looked at that one this weekend.
Right. I have sent all of this information, my public profile on EasyEDA, the website that I designed all these boards on. You guys have access to it, and you can view the projects. You can't do anything to them, but you can view them. And you could copy them and screw around with them if you wanted to. That's completely up to you. You'd have to make an EasyEDA account, but it is free if you have the time. So this board, all it does, the green lines denote, which they're going to be doing stuff in the other room, so I'm going to have to talk louder. The green lines denote interconnections between devices, and anything in a red outline is a component. In this case, the first component, which I'll swing my mouse around over here, this is just a standard connector. It's called a JST connector. It's a 3-pin connector designed to make it so that it's easier and a little bit cleaner to hook boards together. Because rather than me soldering wires directly into a board, it's easier to have replaceable connectors that I can take in and out should something go wrong. These symbols here, where you see like a little triangle, and I'm going to increase the size a little bit just so that the people that are here can see it a little bit better. The little triangles that have the line shooting off them and one flat line on the pointed end, that just stands for an LED. LEDs are directional, which is why they're hooked up in the way that they are. If I hooked it up the other way with the flat line on one side, the LEDs wouldn't work. On the other side, I should say. This is because LEDs are something called a diode. Diodes only allow electricity to pass through one direction. The next symbol here, which I'm going to move my mouse around it, is this squiggle line, is a resistor. Resistors resist a certain amount of energy. In this case, the values of the resistor in this schematic actually aren't right. I didn't change it when I did my bill of materials for this project, but the ones that we are using are fairly close to that number. Resistors resist by turning energy usually into heat. They're not exactly the most efficient way. Well, they, in some way, shape, or form, when you want to restrict the flow of energy, you're creating some sort of resistance which gets rid of heat. And for this instance, they're good enough for what we're doing. And then this little symbol down here, which you'll see probably all the time, where the lines get smaller and smaller as they go down in a triangle shape, is ground. Ground just means that you have a level voltage of 0 that you end at. Now, the reason why we've got 3 connections is because we've got a power connection for the red LED, the green LED, and then in the center we have a ground connection. The reason why we have to have a ground connection as well, rather than just saying it's grounded, is because if all of the components of this battery cart that need to work together don't share the same common ground, the circuit won't work. Stuff won't light up, stuff won't run correctly, communication won't happen.
You gotta like run a ground to the whole cart?
No. Common ground will originate...
Wouldn't it be in the middle?
Well, no. Common ground will originate from the backup battery, which we're using, it's an AGM battery. I can't remember who makes it. I don't know. We're just going to go pick one up at Home Depot. But it's a 7 amp hour battery, standard battery that you probably put in a larger motorcycle or an ATV. They're more commonly used for backup power supplies for computers. But in this case, that is where our ground is going to originate. If all of our components don't connect back to that ground, they're not going to work. Which is the way that this circuit is designed, is that all components end up ultimately back at the same location. So let me see. Oh, of course. Oh, and I forgot. They removed the feature in Chrome that lets you go back using backspace, which is like this is like the one time that would actually be useful. So hang on. Okay, so the next board that we're talking about is the voltage regulation board. Now, I'm not actually going to show you guys the board designs themselves. We'll see them when they come in, which all of you will get the opportunity to see them, obviously, because they'll be actual physical, solid things that you can look at. And we're going to have a lot of soldering to do.
I'm a pro at that.
Yeah, you won't be doing anything until I see you and how well you do at it.
Okay.
You're okay. You sound like you burn yourself a lot from what you've been telling me.
Yeah. I burn myself.
So this is the schematic diagram for the voltage regulation board. Now, really all this does is this takes the 12-volt power from the battery and splits it up into multiple 12-volt channels and down converts it to 5 volts for the devices that use 5 volts. So, obviously, this first bit up here...
So it's like that little box on
So, where does it start and where does it end?
So, technically, that's a good question. Technically, we start right here. In this little symbol that's marked power in, which I can increase the size of this just a little bit if I click on the window. There we go. So, we start right here at power in. Now, power in connects to something called a net. A net is just a way of connecting wires without running them all over the schematic and making your schematic look really crap. It's a little bit easier to visualize when you don't have stuff running all over the place. In fact, the ground symbol, which we saw before, is actually also technically a net. Now this connector right here is just a screw terminal connector. So you put wires into it and you screw them down. And basically we connect to the 12-volt net and the ground net on the 2 different pins, so that way we have a common ground interface and a place to get power from. Okay? Now, in this block right here, this is where 12-volt power gets split up. Now, this is where we have to talk about a concept in electronics, the difference between series versus parallel. Series means that current is the same, and voltage is not. And that's part of the reason why we had to have those resistors in the LED board, is because with too much voltage going through an LED, you can actually blow it up. Think of voltage as like the pressure behind the electric current that you're putting through a wire. In parallel, voltage is the same, current is different. You can think of current sort of as how much is going through. Right, very good. So, you know, you can have low pressure and low current, but you can also have high pressure and low current, or high current and low pressure, because you can change the bore of what you're putting the stuff through. Similar with a pipe. Granted, there are places where the water model breaks down, which is why I'm very hesitant to introduce you guys to the water model, but it seems like Justin already sort of half knows the water model.
Why?
I'm not quite sure. Have I mentioned it before?
No.
No?
Do you know the water model?
But anyways.
Did you break something?
No.
So we've basically got two connectors here connected in parallel. One for powering the Arduino, that's the device that will do all the thinking for the battery cart. And one that is for fan power. Now we're going to have four 4 by 18 amp 3-bay chargers in the back of this battery box. So it's probably going to get a little warm in the back of the cabinet. So Mr. Klein had me design another board, which we'll see here in a couple of minutes, that allows me to control fans like what you'd find in a computer, except these ones are 6 inches across. So we had to do something about temperature control, and so that was the idea, was you just put a fan in each end of the box and move air through the back of the cabinet. Now the next section is this, 12 volt to 5 volt power conversion. Now we've got a couple of different new symbols here. The first one being this one that sort of looks like two flat pieces of red almost touching each other. This is known as a capacitor. Capacitors, yeah, capacitors are what we tell Justin that we're someday going to hook up to a big old battery and have him touch it and see what it does. Capacitors are measured usually in nano and microfarads, and it's just a measurement of how much energy that they can store. In this case, what we're doing with the capacitors is we are trying to level the voltage that is running across the line that they're connected to. So whenever you attach something, well, let's do it from this example. You know how when you're driving the robot around and you're looking at the driver's station console and you see the energy dip real bad when you try to turn?
Yeah.
This is because there is a huge spike in the amount of energy that is required to get the motors to move the way you want them to. Integrated circuits and things that run off integrated circuits are extremely sensitive. You're like
a child, Justin.
To this rise and fall, this constant, I have plenty of energy and then suddenly I don't have enough energy to work. They don't like it. They can burn out. They can stop working altogether for no apparent reason. And it makes life more difficult for the people using the hardware. So these capacitors are known as decoupling capacitors. They just make it so that whatever they're connected to, it tries to level the voltage that's on that line so that it doesn't dip too much, so that it damages the IC. Now we've got one on each side, one coming on the inside and one coming on the outside, because voltage regulators, because of the way they work, they can amplify even small amounts of ripple in the voltage. So you sort of have to protect both sides, otherwise you'll be in trouble. Now, in this case, we actually have two of the same circuit. Now, this piece in the middle here is just a voltage regulator. All it does is a little tiny chip that takes 12 volts and it makes it 5. It's basically it. Not going to go into how it works. It's been a long time since I've had to understand how it works, and me explaining it right now probably wouldn't go so well. But we have two separate circuits that do essentially the same thing, because the issue here is when those circuits convert the 12 volts to 5 volts, they can only do that for a certain number of amps, or how much current we can put through the wire again. And because of what is drawing on those voltage regulators, they're drawing too much for that voltage regulator to handle, so I have to split up the workload. And we see the workload over here. One power connection, 5 volt channel 1, is connected to LED power. It's for those LED boards that I just for the schematic for the LED board that I just showed you. Excuse me. And then the other channel, the channel 2, is for digit power. It's for those digit displays that we're going to be using to actually display the voltage on the battery part next to each battery.
What are you displaying it like? Like little screen?
Yeah. I think I showed it to you last week.
You probably did.
I don't have it with me today.
Like a little calculator.
So, because of how much each thing draws and because of how many we're going to be having all put together on the same circuit, I had to sort of split things up to make sure that there was enough power going to everybody so that stuff didn't dim out and stuff didn't just not work. And of course, as always, all of these connections share common ground. Because even though they're using different voltages for power, their reference voltage, which is 0, where they're supposed to end, is the same. So I gotta pause again because I'm gonna do funny stuff to switch to different. Alright, so we're back. We have to do this in the editor window for this one because for some reason EasyEDA didn't update the image of what I had changed, so we're sort of stuck between a rock and a hard place. Now, this one is a little bit more complicated. Who's Patrick?
Are you referring to SpongeBob right now? You are such
Whatever.
a child.
So we've got to go through this a little bit differently than what I expected to. We're gonna have to use the EasyEDA editor to look at this, which is fine. I mean, it's still gonna look the same as if it were in an image. Just it's gonna be harder for me to navigate. But we'll roll through this. Now, the first thing is power and data input. Now, we've got this power connector right here, which of course tapping on anything doesn't show anybody anything. So I'm circling it right now. That's just general power. That's going to be 5 volts for what we're doing with this board. And we've also got common ground, which obviously becomes important later. This connector right here, just another JST connector. This manages the data. Now, with the shifting board, the whole point behind it was to make it so that rather than having to use 24 data lines to control 24 LEDs, I can use 3.
Oh, that's a good idea.
Now, could I have done it using all 24 data lines?
Yes, but it
Yes.
would look crappy.
It would look really crappy, because that means that I would have had to have designed a board with 2-pin JST connectors, one connection for power, one connection for ground, and done that over and over and over again and just been a pain in the butt. So this actually simplifies the process a lot. Granted, looking at the schematic, there's a lot going on here that is going to not be so easy to necessarily understand, but I'm going to try to explain it the best that I can as fast as I can. Now, if we go over to the left here, we actually see the meat, so to speak, of what actually does the work here. Now, these 3 blocks right here, this one that I'm circling right now, this one here, and this one here, are shift registers. Now, the way shift registers work is you set a data line to either a 0 or a 1, whatever you want that value to be. Okay? You then take a clock line and you pulse it. You turn it on and off. That makes it so that the shift register shifts that bit into a storage space, so to speak. You can do that over and over and over again until you get 8 bits of data in the shift register, 8 ones or zeros. You can then pull something called the latch line. When you pull the latch line, then that serial data that you sent in, that series of 1 and zeros that you indicated by pulsing a clock line, you can then latch by pulsing the latch line, and that will take all 8 values that you put into that shift register and put them out on pins that are actually on the IC itself.
Good deal.
So that way you can turn things on and off. Now, the one thing that's cool about shift registers is that you can do something with them called daisy chaining. If you've ever seen a daisy chain, it's one connected to another, connected to another, connected to another. And each link down the chain can pass something on down to the next link. Okay? Sort of like, you like MacBooks, okay? You know Thunderbolt? The little square connector with a rounded bottom that has a little Thunderbolt symbol next to it on the computer? No?
I don't have a Mac. I have an HP.
But you've never seen it? You
Yeah,
were in the
I've
Mac?
seen a Mac, yeah.
And you've seen the side ports and...
Oh, yeah.
You got one behind you.
Well, that one doesn't have the port on it.
I think he's
Wrong
talking
port.
about the newer Mac.
Newer Macs. Thunderbolt's fairly new.
Yeah.
Thunderbolt can be daisy chained together. You plug one device into your computer, and then on the back of that device is another plug, and you just take another wire, and you plug it in there, and you plug it in the next device, the next device, the next device, the next device, up to, I believe, the newest specification, Thunderbolt 3, I think it's 15 devices. I think. Don't quote me. I think.
So it's like that over there. If you use that as an example, you can use the...
So like if you use...
It's like when you're using like 3 computer screens for one computer.
Right. But you only need one connection on the computer itself. Because you go Thunderbolt to screen, and then screen to screen, and then screen to screen. Right? Okay. So this is the same thing. So as I shift stuff into the first shift register, if that shift register gets full before I pull the latch line, then it will push it onto the next shift register. If those two gets full, then it will shift it on to the third register.
So on.
And so on if we had more registers. But in this case, we only have 3. So in this case, we see some familiar stuff. We've got our voltage in, and we've got our capacitors that keep the voltage level, that protect us from that ripple. And then we've got our 3 data connections, which are over here, which is data in, that's that serial connection of 1s and 0s, that clock line, which times everything when you're actually saving data, and your latch line, which makes it push it out to the actual outputs. The whole concept behind a shift register is taking a smaller number of inputs and creating a greater number of outputs. So in this case, what we do is we create a connection for each LED off the shift registers. Now obviously 12 batteries, 24 LEDs, one red standing for charging, one green standing for charge. We need 24 outputs. Each shift register has 8 outputs. So we just daisy chain them together. And then what I can do is I can use a binary number when I'm programming and just change the bits so that when I push it out to the shift registers, whatever that binary number is what will display on the screen, on the LEDs display. Does that make sense?
Yeah.
It was very, very fast.
It was kind of confusing too, but I get it, but I kind of get it.
For the most part, what you need to understand...
I'm a physical learner, so...
Right. And for the most part, what you need to understand about this is, while you don't necessarily need to know how the shift register does what it does, I know how it does what it does, and I could probably replicate it using different components if I wanted to. But for the most part, what you guys need to know is why. Why did we do this? And it's simply because rather than having to manage 24 outputs, I only have to manage 3.
That's a lot easier.
I mean, that's what, an eighth?
Your life is a lot easier that way.
I mean, there are things that I use for LEDs that I can apply to this concept so that I can make it easy as pie to change what LEDs are on and what LEDs are off, all by using a single number, like a regular decimal number, and converting that decimal number representation into binary, and then doing what I gotta do that way. Now this other thing over here is not super duper important. It's just all of the 3-pin JST connectors that connect to the dual LED boards. Each one is specific to a battery. So B1, B2, B3, B4, B5, B6, B7, B8. And each one has a connection for a red LED and a green LED.
Okay.
Now, of course, I've got to go back and change some stuff here. Give me a minute. Okay, so this next board we're actually in the right schematic for. This one's not laid out as pretty as the other ones were. But it will still work for what we're doing here. Now, the fan driver boards and the board that we will talk about, the fan driver board, not boards, we only got one, and the board that we're going to talk about after this one, these were the ones that gave me the most trouble simply because I was having a hard time figuring out how to deal with turning connections on and off. It shouldn't have been as hard as I made it. I really don't know what I was doing wrong initially, but all of a sudden I figured it out. So, that being said, the first thing, obviously, is our power connection over here. 12 volts, power in, blah, 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 common ground. And then we've got 2 different connections. Now, this is just another form of capacitor. The only thing that's different about this capacitor is that it's polarized.
They all meet in the middle. They all meet in one place.
This here? You mean this here?
Yeah.
Yeah, that's just common ground again. That's all we're dealing with there. But this right here, this is just another capacitor. It's roughly the same. The only thing that's different about it is that this one is polarized, which means that one side has to be connected to positive, one side has to be connected to negative. You hook it up the wrong way.
Close up.
I mean, not spectacularly, but it will get hot and magic white smoke. We also have another thing that looks probably fairly familiar to you. It's this thing right here. Except it looks like a diode, like an LED, right? Except it doesn't have the lines coming on it. That means that it's just a diode. It doesn't emit any light. And then, of course, we have more connectors here and here. And the circuits are roughly the same, just so you know. So I'm not going to go over each one. But basically, the whole reason why this is here, so you know that an electric motor is just a generator that's powered, right? Like you took,
Yes.
You get it?
Yes.
Okay, I'm just making sure, because you're looking at me like, what?
No, I'm like it's like an electric car. How you lift the car.
So, if I went over into the other room and grabbed a sim, okay,
Twist this in.
and I took a multimeter, right, and I had you hold the ends of the multimeter on the positive and the negative connections, and then I took something like a wrench with some tape on the inside of the socket, and I spun the motor really fast, I would create an electric current.
Oh, okay.
As opposed to driving it from the wires to produce a rotational motion on the other end.
I get it.
Okay? So any electric motor can be a generator. That's why in electric vehicles they have that braking system that can restore some energy. That sort of works in the same principle, roughly. And the reason why we have to have that diode there is because it really wouldn't be good if somebody came up and turned the fan the wrong way and backfed energy into the system.
Yeah, that wouldn't be good.
Granted, it probably wouldn't do a whole lot in this instance, just because it's such a simple fan. You'd have to spin it real fast to get it to be a problem. It's still good practice to put that there. The reason why we don't have to do stuff like that in the robot is because the robot has built-in protections for that. Motor controllers and stuff that automatically protect us against, students that come up and push the robot forward as fast as they can. Granted, the lights do come on. That's on purpose because it's trying to find a way to get rid of that energy. Like if you push a robot hard enough and fast enough, the lights on the PDP will come on, and so will the ones on the motor controllers. You gotta be pushing it kind of fast, but they'll come on. And then we've got two other pieces here that are the same thing that are basically switches. Now, these switches are going to be used a little bit differently from the switches that you'll see on other boards here in a minute. These switches are going to be turned off very, very quickly. Well, turned on and off very, very quickly. The reason being is because if you can turn an electrical connection off very, very quickly, you can actually synthetically create a lower amount of energy traveling across that wire. Does that make sense?
Yes.
So there's still going to be power in it after
So,
you
like,
turn it off.
if you think about it, if you think about the water model, let's say I had a valve, okay? And I could open and close that valve as fast as I wanted to. So with the valve open, obviously we're at full flow.
Oh, did you guys do the water thing in CTE? Oh.
So if we're at full flow, then obviously we're at 100% time. Okay? We're constantly doing something. Well, now what happens if I open and close that valve like this?
It's going to let some.
Not only have I reduced the pressure on one side of the circuit, but I've also reduced the amount of current on that side of the circuit. Because I'm cutting it off and starting it, cutting it off and starting it. There's not as much water in the pipe at that point. This is basically the same concept. You're just turning something on and off real fast to try to get a smaller amount of stuff moving through. We do this by a concept called PWM, which we'll be talking about in the second session this afternoon, which, whether or not Alexis will stay for that one, it's going to be much, much longer than this one. This one's actually running a little bit longer, I think, than what I wanted it to. But that one will go a lot more in depth into what PWM is and why we use it.
How long is the second one?
Oh, my battery's running dead. I gotta plug in real quick here.
Maybe you should have charged your lap.
Okay. So this is the second to last board. We're getting there. We're almost done. This is the charger array board. Now, originally, each battery was going to have its own board for managing power connections between the charger and the battery, and the connection that would make it so that we can sense voltage from the battery. The reason why I changed this is because it would have been a lot of boards. This project is going to be expensive enough. The bill of materials that I did for just the electronics, no batteries, no chargers, when I finished it on Thanksgiving, it was $870 freaking dollars.
What?
No batteries, no chargers. So, and my friend Justin and I, not this Justin, my best friend Justin, he and I figured out how much the batteries and the chargers themselves would cost all by the lonesome, and that's like $1,500. So,
Wow.
This project is big. So I was trying to make it so that this was a little bit easier on the wallet. So I combined some boards together to make things a little bit less costly so we could buy fewer of them. Now, in this case, we've got 3 connections for 3 different batteries.
I didn't get home until 5. Leave me alone.
On the top here, we have the battery connectors. One is for the battery itself, and one is for, it's called the sense connection. The sense connection is a connection that goes back to the computer board, the thing that's actually doing the thinking, and on that board is where the actual voltage sensing gets done, which we'll see in a couple of minutes here. We then have another switch, so to speak, for each connection. This just breaks the connection between the charger and the battery. The reason why we have to do this is because when we're charging the battery, there's no good way of sensing what the battery's voltage itself is, because the charger is putting out more voltage than what the battery technically can even store. Without going into how batteries charge too much, basically, when the resistance of the battery starts to go up a little bit, the charger can sense that, and it can shut itself off. In this case, we're doing it a little bit more of a crude way, and just shutting it off when we need to take a measurement. So what we have is we have a JST connector, which will just have digital I/O connections, which means you can just turn them on and off. Nothing fancy. No rapid pulsing or anything, just on, off, on, off. And we put that on the ground connection, technically, between the battery and the charger itself. That way we can stop charging so we can actually take a voltage measurement. Now, I haven't actually decided what the update interval for this product is going to be. Mr. Klein is saying, like, oh, just sense it every minute or something. I'm like, well, that's not going to be terribly accurate. Taking one measurement every minute is not going to work. Really, I'm going to have to take 20 measurements over the course of a second, average them all together, and then display that on the screen.
That's healthy.
But that's logistics on my part, not on anybody else's part.
That sounds fun.
But basically, all we're doing here is making a middleman between the chargers and the batteries. Nothing really extravagant. So now I'm going to switch to the last board. Give me a minute. Okay.
How was there in Boston because I was at a photography thing?
This board is the last board. It's a little bit more intense. You can ignore the warning at the top. It's a reminder to myself to not do something dumb.
Okay.
It says no power should be directly sourced from this board unless you want constant power loss issues. Total power in use should not exceed 200 milliamps. That's more a reminder for myself than for anybody else. Boy, what are they cutting?
Probably,
Oh boy. Anyways, so this board, basically what it's designed to do is bring all of the connections that we need for the battery cart together that need to have something to do with the brain of the battery cart. The actual computer doing the grunt work. Now, in this case, we've got what we're using for a computer is known as an Arduino Mega 2560. I don't have a Mega, I have a Do, which looks very, very similar.
Is that for part 2?
This is for part 2.
I'm interested in this stuff.
This is an Arduino Do. It's not a Mega, but their form factor is actually the same. They look relatively similar, and this pinout is actually almost exact. There are a couple of differences because this chip has some slightly different capabilities than the Mega 256. You want to see it? Yeah.
That one's better. So that one's better than the Mega?
Right. Because that one doesn't have all the connections that we need. Coupled with the fact that it's very easy to blow up a Do, and I don't trust you.
Ha!
So.
Why is that not a shocker? No one trusts Justin.
On this side over here, what we have is the breakout connector. Now, I can't zoom in too much, but basically all that connector
Why is there on this side too?
Is solder connections.
Yeah, but why is there a solder connection on this side?
Because these are soldered to that.
Yeah, that's what those are soldered to. They're pin headers.
Okay. Yeah. They're just confusing.
So, basically what I've done here is this is...
that one's complicated.
It's really not that bad. Is all of these black pin headers, which is this is the same form. This is technically the same form factor as this. All this does is create pins on the board itself that line up with these connectors. Okay? Now, these little blue label things, these are also nets. They're just ways of connecting wires together. Not really super important. This right here is where power comes in to the Arduino. This area right here is where all of the connections for the batteries come in to sense voltages. Now, what we need to sense a voltage is something called an analog connection, which basically means rather than the value being on and off, it can be a range of values. Okay. The way we do this is with something called a voltage divider. If you plugged 12 volts into any Arduino, you would either damage that I/O line permanently, which I thought I did, but I didn't. I realized I just didn't have the right connection stuff.
So you bought an extra Arduino for nothing.
Right. So we have to bring the voltage down to something that the Arduino can read safely. In this case, 5 volts. Now, I've done the math as to what resistors we need to do the voltage division. It's really not something I'm going to get into right now. I could show you guys how to do the math. It's really not hard. Some division and some addition, if I remember correctly. Yeah, division and addition because it's series and parallel. So, but for the most part, it's really not important for what we're doing here. Now, the rest of this stuff is just connectors. So, this is the connector for the LED shifting board. That just breaks out the 3 digital I/O lines that I need to talk to the LED shifting board. This breaks out 2 digital I/O lines for something special called I2C. I2C is a special digital communication protocol that allows me to talk to multiple devices on the same 2 wires. So rather than having to have a whole bunch of connections to talk to the same type of devices, I can have 2 wires and talk to them all on the same channel.
So like CAN.
Like CAN. Very good. Yes. This connector down here just breaks out the PWM connections for the fan controllers. That's all that does. These connectors up here are what connect the switches on the battery charging switches onto this board so that I can turn stuff on and off when I want to. This right here, all it does is sense temperature. I wanted a mechanism that I could use to keep track of the internal temperature of the cabinet, just in case, because when we go off AC power, when we're not plugged into the wall, the backup battery won't last forever. These fans do draw quite a bit of juice. Granted, we won't be off AC power for long, most of the time. If both of these fans were running at full blast, plus all the other stuff running on this battery cart, we could kill that 7 amp hour battery in a little less than an hour. So, I need to be able to keep track of how fast those fans need to be running based on how hot the inside of the cabinet is. If they don't need to be running, I don't want them to be on, because I don't want to drain that battery to nothing.
It's cold in here.
It is cold in here. And that's basically it. So this
It's
is...
so cold in this building.
I don't... It's because it's a metal and wood shop. They probably built this building specifically for this. Never really in the plans for what the school was supposed to be. Just sort of made it work.
Didn't realize, oh,
That's how the
cold in
portables...
the classroom.
That's how the portables at Messalonsky are. So this was the basic... Oh, nice.
Knock over here.
So this was the basic rundown of how...
Can you open that door?
I don't think so. This was the basic rundown of the boards. This is just to give you a general understanding of what everything did. Never really...
I think it makes it colder in here.
It wasn't really intended to make everything perfectly clear. It was just make it so that you could have a general sense of what the battery cart did. That way you could explain it in a very general way. Which is all you're really going to need when you're at a competition. No judge is going to walk up to you and ask you how a shift register works. But that being said, I need to move on to the second part of this for the day. Hopefully all the cutting you'll be able to hear me over. Good Lord, my mouth is drying out. I gotta take a break.
We're trying to figure out